Okay, good evening, everyone. Good evening, everyone, and welcome to the second session of the telescope experiment. So, in the last experiment, we had shown you a demonstration of how the telescopes exactly are, what are the different types of mounts that we use in astronomy, and what all different methods are there to attach your cameras or your cell phones or different types of scientific instruments onto your telescope. Now, we will also quickly revise whatever we learned in the previous session in a 3 or 4 slides. And today we will mainly emphasize on how you can do astrophotography on your own using simple instruments, or let's say whatever instruments you have. So it is a common misconception that whenever you need to do any astrophotography, you will require some very high-tech cameras or very special types of equipment, and many a times it is a block for trying your hand at simple astrophotography. Now, sometimes if you do the astrophotography carefully, you can also extract some meaningful scientific data out of your photos. So many a times people tend to go after taking visually attractive images, which is of course a good idea. But whenever you are doing that, if you take certain kinds of photographs by taking care of the exposure, not overexposing the photo a lot, and using some simple techniques, you can also take scientific observations along with popular astrophotos. Today we are going to talk about both, and we are also going to see what all things are necessary for beginning astrophotography. So we are going to take a very practical and very basic approach of actually clicking astrophotographs and learning different methods. So let's begin. So before we learn about astrophotography, let's quickly revisit some concepts related to photography. In photography, the most important part is you should be able to capture light, and whatever light you have captured should be retained. So in the olden days, the light used to be retained on what is known as a photographic film. So whenever the light used to fall on the photographic film, there used to be a chemical reaction, and from that reaction, the photographic plate used to get exposed, and a part of that photographic plate's color would change, and a slight composition of that plate or the photographic film would change, and whatever light you have exposed it to would be recorded over there. Nowadays, we don't use photographic plates or films anymore. We now have access to excellent electronic equipments, some of which are CCDs, which are charged coupled devices, and we also use CMOS or the CMOSFET sensors. Now, with the help of these modern electronic sensors, we are able to store and record a vast amount of light, which we capture over the lifetime of your camera. Now, in the olden days, you could only expose the camera film for a single photograph, and after that, you would have to use another film. Now, there is no such limitation, and the modern cameras that we use are also very much advanced. We are going to see a slight evolution of how the photography really started and where it is right now. So, whenever you hear the word photography, there are so many different types of photography that come to your mind. And out of these, we are going to focus on one or two types of photography, particularly in relevance to astronomy. So we are going to talk about a little bit of landscape or wide field photography and most part of the astrophotography. Now, in the initial era, the photography or recording a photograph was done by the means of an instrument called camera obscura. So camera obscura is nothing but a pinhole camera or a pinhole projector. So what we do is we use a simple pinhole. That pinhole acts as a biconvex lens, and it produces an image of a very far away object, and that image is real and inverted. This is something that we have learned in our schools and colleges, and we have also done some experiments to understand a little bit more about this. Now, on the right-hand side, you can see a natural pinhole which has been formed from the leaves of a tree, right? And what you see is the image of a sun during the solar eclipse. Now, because there are many gaps in the leaves of the trees, you can see many images of the same object, which is our sun. Now, this is something which is naturally occurring, but you can make some slightly even more sophisticated instruments to get better and clearer photographs and better and clearer projections. So on the left-hand side, there is a sketch which illustrates the camera obscura. It's nothing but a pinhole camera. Then moving further, a camera obscura or a dark room, basically what it does is there is a slight enclosure which allows you to see the image which has been formed very clearly. So it gives you a good contrast, and that is just about it. That is just what a pinhole camera is. Now, from that, we have evolved the camera and the technology for building cameras by quite a large factor. So initially, the pinhole camera used to produce an image, and somebody would sketch along the outline of that image. So that was the general practice. Then there were photographic plate or the daguerreotype cameras. Then there were Polaroids, which are still popular. Then there was an era of film cameras, and eventually from the film cameras we moved on to SLRs and DSLRs. So today the DSLR cameras have another successor, which are the mirrorless cameras, and they have now changed the entire game of photography. It has become really really easy and very intuitive to use these cameras because they give you live preview of how the image would look like, and that is something that is remarkable. So you can imagine clicking a photograph using a film camera, waiting for the film to process, and then eventually extracting the image. So we are not going to spend too much time in the technicalities of how cameras evolve, but we are going to try to talk a little bit more about astrophotography in general. So let's quickly understand the terminologies so it will be easier for us to communicate. So the designs of the lenses and cameras were often inspired from the naturally occurring elements. So like the pinhole was pinhole camera must have been inspired from the naturally occurring pinholes, which are the leaves, the gaps in the leaves of the trees, and then there are so many more sources, right? So similarly, the design of the lens element that you see is inspired from the human eye. So very similar to the eye that we have. Our eye has a hole or an opening in the center, which is called as the pupil. So now this diameter of the pupil keeps on changing depending upon the ambient light conditions. So if the ambient light is too much, then our eye naturally adjusts the diameter of the pupil and it reduces it or dilates it so that not too much light gets into our eyes and we can get a good contrast or we can well resolve the image that we are looking at. Similarly, if we go to a darker location, our pupil opens up a little bit and it allows more light to enter our eyes. So it enhances or it improves our vision in the dark environment. So that is something which is done by our iris muscles in our eyes naturally with response to the ambient light. Now, in case of cameras, there is a front element which covers the aperture of the lens, right? And the aperture is the actual physical opening of the camera, which can be controlled by rotating the lens. Now, most of you must have seen a DSLR camera. If not used, you must have at least seen somebody use it. So I'm sure that you are understanding what I'm talking about. And then there is diaphragm, which moves to physically change the amount of opening. And what does that do? That controls the amount of light that is going to enter inside the camera. So that is important when you are capturing darker or brighter objects, and accordingly you have to change the camera aperture. Now moving ahead, so this actually is just for the sake of comparison of how similar the design of the iris and the pupil of our eyes as well as the lens apertures are. So these are the three important pillars of photography which are known, which is the ISO, shutter speed, and aperture. And we are going to see what all of these individual words mean. And changing whatever settings of the camera, how can you change the quality of the image? How can you change the type of the photograph and all those things? So in the initial session, we had talked a little bit about the camera attachments to the telescopes in general. We are now going to focus a little bit more on some of these technical words. So on camera, you often see the words TV, AV, and ISO written, right? So TV is nothing but the time value or the amount of time for which you would like the camera to expose light. So our DSLR cameras have what is known as a camera shutter. Now this shutter exactly opens like this and closes again. So it opens up for whatever time value you have set, and then as soon as that time value is over, it closes back again. So this is the amount of time for which the actual camera sensor is exposed to light. So that is the physical opening and closing of the shutter. Then there is the aperture value. The aperture is the actual physical opening that you saw in the earlier image in the lens element. So that controls the amount of light entering the camera. All right. And then there is ISO. So ISO is the amount of amplification that is applied to the image later on. Now, ISO in the digital cameras is very much different from the ISO in the earlier lens type cameras or film type cameras. For films, you used to physically needed to change the film that you are using depending upon the different grain size. Okay. So by grain size, I mean the densities of the films were kept different. So a higher density of film would be more sensitive to faint light than a lower density film. Now, in case of digital cameras, you cannot physically change their density as per your requirement, right? What you do is you apply a little bit of a digital signal processing on whatever image you have acquired, and that digital enhancement or amplification is known as ISO. It is the ISO setting for camera. Now, changing the camera's ISO to a higher value is the same as increasing the intensity slider in your Photoshop or your Lightroom software. So, if you don't use these softwares, there is an alternative free open source software called GIMP, called GNU Image Manipulation Tool. All right. We are going to see these softwares also in detail. And I'm going to enlist all these softwares. And at the end of this session, we will share this presentation with you. So, all three components, when put together, they produce the final image, right? So image is a combination of the shutter speed, ISO, and aperture, and all three settings, whenever they are used in unison with the appropriate and the most perfect amount, you can get the best clear possible image, right? And of course, you will have to focus your image with the help of the lens, and the lens element itself will move in order to match the focus with the sensor. So that is yet another skill that will be required, and that will always come better and better with practice. So this is the exposure triangle that you popularly see in most camera books. It just has the definitions that I already told you about. So this is the exposure triangle, which is a combination of shutter speed, aperture, and ISO. Then this is a chart which gives you a correlation. So what happens to the image when you change different elements, right? So on the left hand side, you can see the lowest aperture, and on the right hand side, you can see the highest aperture. So as you increase the aperture, the depth of field changes. So for the lowest aperture, the far away objects are focused. For the highest aperture, the closer objects are focused. So the large aperture gives you a higher depth of field experience. The low aperture gives you a low depth of field experience. The depth of field, I mean, the closer subjects are focused and the farther subjects are blurred. So that gives you a sense of depth of field. It gives you a sense of, which object is closer and which object is farther. So depending upon which part of your frame would you like to focus, you will have to choose the optimum aperture. Then ISO is the overall amplification of the image that you would like. So using a higher ISO in a darker environment is a good idea. So it enhances the overall light of your image. But the problem with increasing ISO too much is it also increases the noise. We are going to talk a little bit more about that. And then the shutter speed is the actual amount of time for which the camera's shutter is open. So these are the combined, elements or the elements of the exposure triangle. Then these are some analogies that we have used. So this slide is kept to give you an idea how the aperture number corresponds to the aperture opening. So f1.4 is nothing but the focal ratio. And this is something that was discussed in the experiment session 1. So we had talked on how to calculate the focal ratio of a telescope if you know the aperture and the focal length. So focal ratio is nothing but the division of focal length divided by aperture. In case of your camera, you can tell about the aperture of your camera by looking at the lens. So when you take your camera lens and you look in front of the lens, there are these numbers written over there. So on the left hand side, you can see a circle with a cross in it, right? A phi shape, which tells you the outer diameter or the aperture of your lens element, which is 77 mm. Now on the bottom, you can see 24 to 70 mm. That is the range of focal lengths that your camera lens can adjust to. So you choose any focal length, and if you divide it by the aperture of your camera, then you get a focal ratio. So what they have given here is 1 is to 2.8. So this value is called as the focal ratio value, and this focal ratio value is given for the lowest focal length of the lens. So on this particular lens in the image, for 24 mm focal length, the minimum aperture that I can set is 2.8, which is f2.8. So that is the meaning of these numbers which are written over here. Coming back, the smaller the aperture, the smaller the focal ratio, larger is the physical opening or the aperture. So f1.4 means f divided by 1.4, which gives me the equivalent aperture value or the equivalent aperture. So if I divide the focal length by a larger number, the fractional answer, the answer of the division will be smaller, right? So my aperture size will become smaller. What I'm trying to say is, smaller the focal ratio, larger is the aperture. Larger the focal ratio, smaller is the aperture. You can clearly see in the image as I've already shown. The focal ratio values are known as f-stop numbers in the language of photography. Both of them mean the same thing. Some photographers also call it as the f number. So these are just given for your reference. Now, we also talked about what all of these numbers which are written on the lens mean. So the 24 to 70 mm is the range of the focal length that you can use with this particular lens. The diameter of the frontal element is given on the top left, and then the focal ratio of the lowest focal length is often mentioned on the lens. Then we also talked about this. Changing the f-stop changes the depth of field of the image. So larger aperture will focus closer images and defocus farther images. Keeping a low aperture will often focus both images. So you must have experienced this firsthand. If you want to see a farther object very clearly, what you do is you tend to squint your eyes, or you pinch your eyes a little bit, and then you are able to focus objects which are very far away, especially during daytime. So that is something that we are doing with the camera here, but our eyes tend to do this thing naturally. Then shutter speed is the actual amount of time for which the camera shutter is kept open. So I know we are purposefully repeating this again and again to give you a good idea. So this is the overall shutter actuation process. What I mean is, the light coming from the sources enters the camera element. The light gets focused with the help of different lens elements present inside the lens, and from which it enters into the sensor. Right? The light will only enter to the sensor if the shutter is open. If the shutter is closed, the light will not reach the sensor. What will happen to the light then? As long as the shutter is open, the light will reach the sensor. If the shutter is closed, the light will get reflected to the viewfinder using a mirror. So in front of the shutter, there is always a mirror at a 45-degree angle. So whatever light enters the lens goes on the top towards the viewfinder, as you can see in this image. And from that viewfinder, you can see the image through the eyepiece, which is given on the back of the camera. So these are the different effects of shutter speeds. So a faster shutter speed, meaning low time value, right? So the shutter speed, if you set the time value as 1/10,000th of a second or 1,000th of a second, then you can capture still photos of very fast moving objects. Like you can see examples given here. So if you drop a water drop in the pond or maybe a glass, you can capture a still frame of a water droplet, or maybe you can capture still photos of sportsmen who are moving very fast. So this is the use of the high shutter speed. Then there are mid-range shutter speeds which are used to capture objects moving with a slow speed. And you can also use this vibration correction setting on camera lenses, which allows you to capture photos with minimal shake. And then in astronomy, we use the long shutter speeds, which are greater than 1 second. So our time value is often 1 second or more, sometimes as long as a few hours or as long as a few minutes. And when you integrate the timing of a few minutes or few hours, you can capture beautiful details of galaxies, clusters, or nebula. So in the front of you, you can see the Milky Way long exposure image, which is around 1 minute exposure, and this was taken at Lagoon. And this is a single photo, and in that single photo, we have been able to capture the Milky Way galaxy band. Also, we have been able to capture the reflection of some of the stars in the water body, and then some landscape. And on the right hand side, you can see a light painting. What we have done is we have light up a small fire wool, or it is also called as glass wool, and we have attached it to a string, and then we have rotated it to give us an effect of burning ring. So it is basically a long exposure photograph, maybe of a few seconds, maybe 10 or 15 seconds. And in those 10-15 seconds, the sparks which were flying from that wool have flown, and they have traced this line over here, the arcs over there. And in the center, there is a bright ring, which is a long exposure of that wool attached to the string itself. So ISO, like I said, is actually nowadays it is not the physical density or the grain size of the sensor, but it is the amount of amplification that camera applies after acquiring the image. Correct. So in astronomy, it is always a good idea to capture an image with a lower ISO because you can digitally enhance the image, but you cannot reduce the light which is already captured by your camera. So it is a very, very important thing to note. So if you increase the ISO too much, then your light is enhanced, no doubt. But often, along with the light, noise is also enhanced. So noise is basically the unwanted signal, which is a result of the noise, which is the result of the temperature of the camera sensor. If the camera sensor is too hot, the high temperature itself is captured like a signal on your camera sensor, and that is called as the thermal noise. Then many a times, if your camera is used too much, then some of the pixels on your camera are dead, or they become permanently exposed, and they give different colored aberrations called trichromatic aberrations. So if you zoom in your camera image quite a lot, you will see some permanently red, blue, and green pixels. So those are known as trichromatic aberration. And because of these things, by using too much high ISO, the overall dynamic range of your photo changes or it reduces. The dynamic range is the gap in between the black and the white colors. So if you want to produce an excellent image, you need the best possible contrast. And for getting the best possible contrast, what you need is a high dynamic range. So it is always a good idea to use the optimal ISO, not too low and not too high. So that comes with whatever the ambient light conditions are, and also depending upon the object that you're capturing. So many a times the color is a very, very important factor when you're doing astrophotography, because you would like your objects to be as colorful and as wonderfully captured as possible. And in order to capture the right kind of color, you need to set the white balance of your camera appropriately. So depending upon the time of the day, light conditions, and the temperature of the object, temperature by temperature I mean the color of the object, you should be able to choose the white balance. So there are different types of white balance settings in your camera. There is also another fifth kind of a setting called custom setting, which you can control by changing the temperature of the camera. So the temperature is basically the Kelvin value of the color that is given in your camera settings. And different colors or different white balances are chosen to to overall change the mood of the image or overall change the effect of the image that you are capturing. So this white balance comes into picture when we are capturing daylight images or wide field images in addition to astrophotography, because many a times you often need a good foreground to have your astrophotograph along with. So to choose the best possible foreground, choosing the right kind of white balance helps. Then different types of camera sensors are there, which which have their own advantages and disadvantages. So the full frame cameras are same as the film cameras, which are 35 mm in size. So they give you the entire full frame of whatever light is coming through the lens, right? So those are known as full frame cameras. Then there are crop sensors, which are smaller than size than a full frame. So what these crop sensors do is they only capture a part of the light which is entering the camera. So they give you an apparent magnification. So when you see a part of the image as compared to the full frame image, then you get a effect of overall magnification. So whenever you use a crop sensor, you can get a slightly magnified view of the same image as compared to a full frame sensor. This is an example over here. On the left hand side, there is a full frame sensor using which I have used a full frame camera along with a 50 mm lens, and I have been able to capture this entire landscape, which has 1, 2, 3, 4, 5, 6 mountains, some trees in the background, and sun and the clouds. Right now, I can also see a couple of mountain ranges. On the right hand side, I have used a crop sensor, a camera with a crop factor of 1.5. So what the crop factor 1.5 means is, since the sensor size is smaller, the effective focal length that I get is multiplied by the crop factor. So if my focal length is 50 mm, for a full frame, my crop factor is 1. So 50 multiplied by 1 gives me an effective focal length of 50 mm. In case of a crop sensor, the crop factor is 1.5 or 1.6. So the 50 mm focal length lens is multiplied by whatever the crop factor we get, and we get an effective focal length which is more than the original focal length. So you get an effect of magnification because of your smaller sensor size. So you see only a part of the whole image rather than the whole image itself. So there are two types of lenses which are used in astronomy. One of them is called as a prime lens, which have a fixed focal length. They are simple in design and slightly cheaper. Then there are zoom lenses, which are slightly versatile because they have variable focal length, and because they have variable focal length, they are also a little bit expensive, heavier, and more complicated. Nevertheless, if you want to do wide field photography, I will recommend you to go for prime lenses. But if you want to do different types of photographies and capture and buy one single lens, go for a zoom lens with the least possible aperture that it allows. Then this is a very important chart. We have seen this in the first demonstration as well. This is a chart which gives you a relation between the focal length, magnification, and the field of view. Right. So for a DSLR camera, if you use a 11 mm lens, the focal length is 11 mm. The field of view that you get is almost 180 degrees. So you can capture the entire area in front of the lens. Right. So as you keep on increasing the focal length of the camera, the field of view keeps on decreasing, which is nothing but logical. So the more you magnify, the smaller the area you focus on. The smaller the area gets. So that is what happens when you increase your magnification. So the chart beautifully represents as the focal length increases, the field of view decreases and the magnification increases. So that was the brief introduction of photography in general. So now we have another half an hour. I'm going to talk a little bit about astrophotography in the next 10-15 minutes. And after that, we would like to show you actual observations and how to actually observe the moon as well as the sun. So today, unfortunately, the sun does not have too many sunspots. Actually, it has only one sunspot, and it is also on the eastern limb, and we are not able to see it clearly. We will also talk about how to know whether there are sunspots on the sun today, and how can we safely observe them and capture them. And if we safely observe the sunspots regularly, you can tell the speed of rotation of the sun. You can also tell when and how many sunspots are being formed on what part of the sun. Right? So there are different types of observations that you can do. So any camera that you have access to is virtually or potentially an astrophotography camera, because you need to build some attachments or you need to do some jugaad or adjustments in order to attach your camera to the telescope. But once you have done that, then you are able to use any camera to do astrophotography. So I myself have tried astrophotography using all of these cameras that you see on the chart, right? So we will be able to tell you or help you take your own astrophotographs using any of these cameras. So in the initial session, we already talked about this. You have seen this adapter first time. You have seen the T-ring adapter that I had attached my DSLR camera to the telescope last time. And we also had shown you the mobile phone adapter and a live view of the telescope during our last session. So we had shown you the building on the opposite side of IUCAA. Today we are going to do the observations of Moon. We are going to try and see the lunar craters. You will see the lunar craters, especially in the daytime, and you will notice that the features of the moon that you see in the daytime are much different than what you see in the nighttime. We are also going to show and demonstrate how to observe the sun safely using solar filters. And this is very important, because unless and until you don't use solar filters, you will no longer be able to use your phone if you observe the sun directly, because the sun will permanently damage your camera sensor, and it will either burn it or it will permanently damage all the pixels over which the sun's image is formed. So be very careful when you are doing astrophotography, especially of the sun, and be even more careful if you are observing the sun with your eyes, because it is very dangerous if you are not using the appropriate solar filters. Then there is this eyepiece projection assembly as well. This is something also that we talked about last time. And then there is another type of mounting called piggyback mounting. So this bolt that is given on the bottom is just like any other tripod bolt. So you must have seen camera being attached to a tripod. So this is exactly like that, but instead of a tripod, you are attaching it directly onto the top of your telescope, right? So whichever area the telescope is looking at, the camera is looking in the same region. But the advantage of using a camera along with the telescope is camera will be able to give you a wider field of view, and you can change the camera lenses anytime to control the field of view as well as magnification, which is not very easily possible in case of a telescope. So in astronomy, whenever we capture images, we often select the camera settings to be RAW. So in case of Canon, the RAW format is CR2. In case of Nikon, it is NEF. So no matter which kind of camera you are capturing, choose the highest possible resolution of the photograph that you are going to capture. And the reason is whatever file format your camera is going to store, we want it to retain as much amount of light as well as color information that it can. So if you are capturing using a simple web camera, we will suggest using a 16-bit or 24-bit image rather than an 8-bit image, and try to store maybe a PNG image instead of a JPG image, or maybe a BMP image instead of a JPG image, which will retain the color and light information that it captures. So these other types of raw images that I mentioned are, what they do is they save the light information and the color information in lossless format. So whatever light and color has been captured by the sensor, that data is stored as it is. In case of JPEG or other file formats, a little bit of compression is done to reduce or to optimize storage space. So what happens is, many a times the important data which is captured gets compressed and perhaps sometimes lost. So if you want to do some important processing or some meaningful scientific observations with your data, use a raw setting with your camera and to store the images. So different types of images that you can take are star trails. So sometimes the star trails are favorable, sometimes they are unfavorable. So if you want to capture long exposure images of galaxies or star clusters, then you don't want images to have star trails. So for that, to get rid of star trails in the images, you have to choose the optimum exposure. Okay? So there is this thumb rule. It is not an exactly accurate exposure value, but it is called the 500 rule. So divide the focal length from the number 500, and whatever answer that you get is the optimum exposure up to which you can expose your camera without getting star trails. Now, mind you that this is a very crude and very simple thumb rule. It is not at all very accurate, but this is a very practical approach, or it is a very practical solution to choose the optimal exposure. So let's say if you are using a 20 mm lens, then for a 500 using the 500 rule, you can give a maximum exposure of 25 seconds, up to which you will not get star trails, right, in a exposure. So the maximum amount of exposure that you can give is 25 seconds, up to which your camera will not produce star trails. So I'm of course talking without taking tracking into account. So if you are using a tracking mount, then there is virtually no limitation. But practically, it depends upon how well you have aligned your mount and how well balanced it is and everything. Coming back, so let's say if you get an answer as 25, giving a 20-second exposure is always safer, and it will be ideal to capture photographs without star trails in it. All right. So the star trails, I mean these kinds of star trails I'm talking about. So this is a single exposure of Milky Way, which is 30-second exposure. So in 30-second exposure at 15 mm focal length, I'm getting slightly some amount of star trails, right? So if I had used this 500 rule, then I can get the optimal exposure, and it is a good idea to subtract 5 or 10 seconds from the calculated exposure to get the appropriate shutter speed up to which you will avoid these star trails. So you will get a very well focused and sharp image. So if your camera is a very high megapixel camera, which has too much pixel density on the sensor, then this rule may not always work, and it does not work with the medium format of the camera. So if you're capturing images using the large format or the raw format, this will work. It does not work with the medium format. And if you enlarge your image a lot, then the image quality gets, the star trails get enhanced or they get enlarged too. So it is not ideal in that case. So to take into account all of those things, this is a more sophisticated way to calculate the optimal exposure to capture sharp stars. So I know that this is a little bit complicated to look at, but it is not at all very difficult to understand. So the formula is such that 35 multiplied by the lens aperture, that is one value, plus 35 multiplied by the pixel pitch. Okay, so the number 35 is taken for a full frame value. So we are going to adjust the formula depending upon the type of the camera that we are using and the type of the lens we are using. So the formula is 35 times the lens aperture plus 35 times the pixel pitch divided by the lens focal length. So the lens focal length can be seen by looking at the lens. The lens aperture can be seen by whatever aperture you have chosen, right? Then the aperture is nothing but the f-stop or the f-stop value that you have selected. So you know 2 out of these 3 things. What you don't know by default is the pixel pitch. So pixel pitch is basically nothing but the gap between 2 consecutive pixels. Now, the one way to find out the pixel pitch is do a Google search and find out the pixel pitch for your camera. Another method is calculating it once and for all. So pixel pitch can be calculated by taking the sensor width divided by the number of pixels into 1000, right? So now this value can either be found along with your camera manual, you can find it online, or we have existed pixel pitches for 20 popular cameras that we have, right? So these are the pixel pitch values that you need to substitute in that formula. So 35 times lens aperture plus 35 times the pixel pitch divided by the focal length. So the example is given over here for a camera with a 24 mm focal length and f2.8 value. So if we substitute those values into the equation, and the camera is given Canon 5D Mark IV. So if we refer this table over here and substitute that value into this formula, we can get an exact and accurate value of the exposure up to which we can expose the camera without getting any star trails, or we can get exactly sharp star images. So this is a very good tool or a very good formula for calculating the optimal exposure. The next solution is to use a tracking mount. So a tracking mount will allow you to track objects for 4 or 5 minutes or even longer, depending upon the focal length that you're using and the quality of the tracking. So using an equatorial mount that we had seen in the last session will give you the best possible tracking experience, because if you're using an ultra azimuth mount, you will get what is known as field rotation in your image. So to avoid that, it is a good idea to align your camera axis to the Earth's axis and then track the camera in the same direction at which the Earth is rotating, right? So you will keep on looking at the same area of the sky as it moves from east to west because the mount is rotating at the same speed. And then you will be able to capture the image for a longer and longer period. So this is an example of Lagoon Nebula which was captured. So you can see this is the equivalent 25-minute exposure. Now the camera was not looking continuously to the sky area for 25 minutes. We have taken 5 photos, and each photo is a 5-minute exposure. And then we have stacked those photos together using some softwares, and then we have enhanced the image, the intensity as well as contrast a little bit using some softwares. So this is the equatorial mount that you should use when you are thinking about doing astrophotography. So this will give you the best possible results. It will also allow you to expose the image or expose the frame for a longer amount of time as compared to an ultra-azimuth. This is just to give you an idea of the field of view. So this is the Milky Way band taken near the Sagittarius constellation. So I'm sure you must have heard and learned about the constellations as well as different zodiacal constellations during the course of this summer school. You also have already been introduced to stellarium, so which is an excellent tool to learn about constellations, different stories, also understand the positions of different objects in the sky. So you can use stellarium to plan what kind of photography you are interested to take. In stellarium, you can set different cameras and you can get a field of view of whatever region you want to capture. So this is the Milky Way. With a wide field, you can capture almost most of the part of the arm. Using a 35 lens, you can only capture the central arm or the central galactic center of the Milky Way, which is very close to the Sagittarius constellation. So this is a very, very interesting and a very powerful tool, stellarium, I mean, using which you can plan such images and then you can try executing your astrophotography session later. So the focal length for Milky Way is compared here. So for different types of cameras, to get the same effect, you would have to compensate the focal length as such. So for a 24 APS-C camera, which is a crop sensor, you will get an equivalent focal length of 35 For a 60 micro sensor camera, which is 4:3 ratio, you will get the equivalent focal length of 35 So this is what I was telling about the crop factor in the initial part of the presentation. So then there are some defects that you experience. There is something called chromatic aberration, which produces a little bit of colored rings around the object. This also happens if you have bad quality spectacles or even a bad quality windshield on your car. So when you're traveling in the rain or in the night, you can often see colored rings around objects, which are known as chromatic aberration. Then there is spherical or chromatic aberration, which is observed in case of deformation in the lens. And then there is astigmatism, so which happens in case your lens is cylindrically deformed. So these are the different defects that you can experience. And then there are different techniques to reduce that. One of the techniques is to reduce the aperture size. So the defect is also reduced. So there are different techniques that you can read about. So you can also follow through how to fix these defects, how to detect these defects, and what kind of faults are there in your lenses. So those all things can be found out using these different types of aberrations. So this is the general process for astrophotography. We locate the object, we take the sample photo, make sure the object is at the center, and then we capture multiple frames of the object and stack them and process them. So this is the noise that I was talking about. So if I give a very, very long exposure by covering the camera, I am still able to capture this kind of signal on the camera, right? So this is an undesirable signal, which we call as the noise. And this particular type of the image is known as a dark frame. which we capture in order to capture all the thermal and the trichromatic noise. So once we have captured this for the exposure that we are going to capture, we have a subject frame now, which we can subtract from the photo that we take. So from that photo, all of this noise will be subtracted, and whatever will remain will most probably be the light coming from the source. So that is the idea. So a signal to noise ratio is nothing but how powerful the signal is compared to the noise. More the SNR, better is your image. So by stacking, what we do is we boost the signal to noise ratio, we average out the unwanted noise that we have, and we tend to produce a cleaner and a sharper image. So this is the clear example. This is a single image of Milky Way, and these are 5 images which have been stacked together. You can see that many more stars have been captured. The noise has been significantly reduced, and you can also get a good SNR and a good color overall effect in your image. So this is the power of stacking your image and being able to generate much more higher resolution and much more clearer images. So this is the overall flow. We take a single image, we stack those images together, and then we process the image a little bit by changing its intensity and a little bit of saturation and other values. So these are the different softwares for camera control. For Canon, you can use EOS Utility and DSLR Remote Pro. For Nikon, there are these softwares MK Remote, and there is this Digicam Control, which is a free software compatible for many cameras, many different models. For stacking, you can use the following softwares. So I have just enlisted them. You can take a look at these softwares later on. We are not going to go through this entire process today. But if you are interested, you can always write to us and we can share you the documents. Or there are more than enough tutorials on the internet which will help you learn how to acquire and process these images. So in another 1 or 2 minutes, we will wrap this presentation up and we will move to the demonstration session. So let me just check if our demo team is ready. Santosh, can you please make Tushar co-host? Okay. So for processing, you can use some of these free softwares. So whatever softwares that we have tried to enlist, we have tried to include only the free or the open source softwares, so that you don't have to subscribe or pay for any. And it is also always a good idea to promote these, and it is always a good idea to write your own, action sets and write your own tools in order to process your own images. So these are some softwares that you can use for post processing, out of which the Registax and the Lightroom CC is free. The other 2 are paid. Using different techniques, you can capture beautiful HDR composites of moon. So these are some examples of the lunar photography that I've done. So you can always capture different phases of the moon, and you can capture different features of the moon in much more clarity. So during the second quarter moon, you can capture the craters near the mid region of the moon. You can also capture some mountain ranges, and taking composite is nothing but taking a low exposure image, taking a mid exposure image and a higher exposure image, and putting those images together. So a higher exposure image was used to enhance the non-illuminated vision of the moon. Then a low exposure image was used to enhance the high illuminated vision of the moon, and a nominal exposure was taken to enhance the craters of the moon. So these 3 images were put together and a composite was made. Now, what we have done is we have also taken an image of the crescent. So today we will see a slight crescent of the moon, and that image will be in the data. So let me just check. Tushar Dada, are you ready to show the setup?
Yeah, I am ready.
Okay, so we will
My
start.
video.
Yeah, just a second. I'll have to give you the permission. Just a second. Now, can you check?
Okay, it's
Yes.
working.
Yes. I'll stop sharing for a moment. After this demo, I will show you some more images. We will come back to this presentation. I will now spotlight Tushar Dada. So yes, we can see you and hear
Yeah.
you as well. So we are at the terrace of the IUCAA Science Center, which is just outside IUCAA. Now you can see this telescope has been connected with a solar filter. Now this telescope lid has been covered, and on the opening a solar filter has been attached. We are now going to set sun and see if any sunspots are visible.
Atharva,
Ah,
the sun is not visible.
okay.
It's completely
So
cloudy now.
it's
Oh,
overcast right now. So
overcasted.
perhaps
So
we can
I
try
will
to see moon.
just go on to the moon.
Okay, great. So today there are no sunspots anyway. So by the time we setting moon, let me quickly show you. So I will share my screen again for a moment. So this is the website that you can use for getting real-time images of the sun. So this is the latest image of sun. So you can click on the sun now. So this website is soho.nascom.nasa.gov. And on this website, you can get the most recent image of the sun captured by SOHO telescope, which is Solar and Heliospheric Observatory. And you can see in this image over here, there are almost no sunspots. There are quite a few, but they are very, very tiny. So it is going to be very difficult for us to spot these sunspots using a small telescope that we are using. Let's go back to the telescope setup. And now let's try and observe the moon. So note that we are going to show you the moon through a mobile camera. The mobile camera will be looking into the image produced by the eyepiece. Now, the eyepiece that we have used is a 25 mm eyepiece in combination with a 650 mm diameter telescope. So, those of who you are watching or who are in the meeting can immediately figure out what will be the magnification. So, we had already discussed the formula of magnification. There was also a test that was conducted, I think, this weekend, right? So, there are some questions related to magnification and focal ratio. So, I hope that you have not forgot the formulas, and I hope that you still have those in mind. So, the focal length of the telescope is 650 mm, and the focal length of the eyepiece that we have used is 25 mm. So perhaps you guys can immediately figure out what the magnification is. So Tushar, as soon as your moon is set, you
Yeah,
can
just a moment. Just a moment.
all right, no problem. So today we are going to see the moon in daytime. We are going to see some craters of the moon, and we are going to see two parts. So one is the well lit area of the moon, which is receiving direct sunlight, and other is the part which is not receiving sunlight. So these parts are divided by a line which is called as a terminator line, which divides the bright and the dark side of the moon. Right? The dark, I mean the non-illuminated side. And along this terminator line, you can get a very good contrast, and because of that, you can see a lot of craters as well as mountain ranges on the moon. So we are going to see that very soon. And you can do this very easily with any small telescope as well. So moon is a very, very big and a bright object, and it does not require some excellent optics to see moon. You can use it with you can view the moon with even a very small binocular or even a small monocular like Galileo used. So Galileo only had a 50 mm diameter telescope, and using that telescope, he observed the phases of the moon, the different positions of the Jupiter's moons, and then he also discovered that the Jupiter's moons revolve around the planet. Yes, we could see the image of the moon. The moon is slightly drifted towards the right hand side of the field of view. We might have to bring moon to the center. So now he is showing you the handheld image. But in the last session, we had shown you how to use the mobile phone adapter and how to use a DSLR camera. So we can see the moon in the field of view, but we are not able to see the details of the moon right now. He's trying to bring it to the center. Just trying to set it up again. Right now, even the conditions in Pune city are quite cloudy. So because of that, the image of the sun could not be shown. But we are going to try and attempt to show you the moon again. So he's using the finder scope to spot the moon. And as soon as the moon comes into the crosshair of the finder scope, it gets aligned with the field of view of the telescope. And then we're going to magnify it using the IPS. In the last session, we had shown you how to connect the camera using a mobile phone adapter, and a DSLR camera was connected using a T adapter or a T ring adapter. So while he's setting it up, I will quickly come back to the presentation. I have some images that we had captured in our last session. Let me show them to you. So I hope the screen is again visible now. Now, these are some of the close-up photographs. The one on the left-hand side is taken using a DSLR camera, which was attached to the telescope. And on the right-hand side, this was taken during some other phase of the moon, where the details of the mountain ranges and craters have been very nicely captured.
Yeah, Atharva.
Yes.
Got it.
All right. Let's quickly see the live image. Yeah, you can see the moon now. Can you zoom in digitally a little bit more? It is not very focused right now. I think it is also a little cloudy.
It's a hazy.
Yeah, it's hazy.
So that for
There is also a little bit of a lag.
but the sun is completely gone.
Okay, no problem. There are no
Yeah.
sunspots today anyway, so I think everybody got an idea how to observe the moon through the telescope. In the last session, we had purposely shown you the attachments because today there was a weather uncertainty. Usually, the monsoon starts in Pune city around 6th or 7th of June. So we had shown the attachments of different telescopes in the last session itself. So I quickly want to show you a couple of more photos. So these are some photos taken using simple cell phones, similar to how we just saw right now. We have taken these photos by handheld phone held in front of the eyepiece of the telescope. So it is that very simple to observe and capture the photograph of moon because it is a very bright and a very large object. So it becomes very easy to spot it, track it, as well as capture it. So with a little bit of practice, you can capture better and even more clearer photographs of moon. So many a times a good technique is to take a video, and from that video you can extract a couple of images and select the best possible images and process them a little bit to produce these high resolution moon images. So these were taken using a simple mobile phone. Then this is a simple moon photography cheat sheet. It requires there is a small checklist which you can refer, and using this checklist you can be ready to capture the photograph of the moon using whichever camera or whichever device you have. Then these are some examples of planets that we have captured using different types of cameras and telescopes. So all of these planets were captured using a planetary camera called ZWO. So similar to ZWO, there are similar models of QHY. Then there are SBIC cameras. So you can choose any camera which is in your price range or whichever is accessible to you. most colleges and universities have these cameras nowadays. So perhaps you can find out the nearest astronomy club or college or university, and you can capture beautiful images like this. So the planets are arranged in the increasing order of their positions. So there is Mercury, Venus. You can see Mercury is in a gibbous state. Venus is in the crescent phase. You can see Mars with its polar caps. Then there is Jupiter with its great red spot. There is Saturn along with its ring, and then there are you can see the Cassini division as well, which is the gap in the ring of the Saturn. Right? Then there is Uranus and Neptune, and along with Neptune, there is another object which is its moon called Triton. So you can capture almost all of the planets in the solar system using a simple small telescope with a considerably large focal length. So these are some planet photos. This is a photo of Jupiter and Saturn conjunction, which was taken last year. So Jupiter and Saturn both were in the same field of view of the telescope. So this is a single image. Then you can capture photographs of comets, which are not very frequent visitors, but once they visit, as soon as the comets get closer and closer to the sun, the brightness increases and the size of their tail increases, and you can capture images like this. For wide field photography, the Star Stacks is a free and a beautiful software which you can use for stacking the images that you have taken. So you can take long exposure images or many long exposure images, and you can stack those images together using this software. So this photo was taken at the IUCAA Observatory, and this was taken around 5 or 6 years ago. And you can see these red colored dots or tails. Those are basically the aeroplanes which have flown through the field of view during various times. These are some more examples. These are taken using simple cell phone cameras. So nowadays, even cell phones are capable of capturing beautiful photographs like this. Right? Then these are some more examples of cell phone photos. So no DSLR camera is used. Then this is a DSLR image captured with Canon 760D. This is a long exposure image. These are 10 exposures of 2 minutes each. And you can see this is very bright spot over here. That is planet Jupiter. And all of these others are stars. There are some clusters over here. There is a nebula over here called Trifid Nebula. So beautiful images like these can be captured. This is taken only using DSLR. No telescope is used. These are some more exposures of simple camera and lens images. 10 exposures of 30 seconds each are given using a 10 mm lens and a f4 aperture. So all the settings are also given here. I'm going to share this presentation with you along with a couple of more documents, which you will find useful if you want to try astrophotography and also some small projects on your own. Prakash has also shared a document of using stellarium more effectively. So I will encourage you to go through that document and try to explore all of the features as much as possible. So these are some examples of wide field satellite photos. I'm only going to show you a couple of more photos and then we're going to stop. These are the photos of meteors. The the drawback of capturing meteors is you cannot predict whether a meteor is going to pass through your frame or not. You just have to be lucky because you do not see a meteor in advance. So whenever the meteor passes through the atmosphere, it burns out, and then and only then is it captured. So you cannot really plan a meteor photo. But yes, during a meteor shower, the probability of capturing a meteor is very, very high. So if you do wide exposure photography during a meteor shower, there is a chance that you will capture many meteors as compared to a day without meteor shower. You can also capture photos like these. These are 1, 2, 3, 4, 5, 6. 6 photographs of the same area taken after different intervals of time. And then all of those 6 photos were put together to produce multiple images of the sun. So these types of photos are called as time-lapse photos. So if you put too many photos together, one after another, you can also create a time-lapse video, right? So this is an example, or this is a photograph taken during a lunar eclipse or a total lunar eclipse. On the left-hand side, it is taken during the sunrise. You can also do some time-elapsed photographies. This is where the white balance comes into picture. So the white balance controls the overall tone or the color of the image. So depending upon the light and the time of the day, you can choose different white balance settings to give to get a nice feel or to get a optimal color tone for your image. So this image is taken from a single point. So four images were taken from a fixed camera point, and parts of those images were cut, and different parts of different four images were put together to match the skyline. So this is called a time elapse photography. This is just a artistic representation of different times of the day to give a combined effect, and also to understand the changes in the sky and changes in the positions of the object. So you can also do solar photography, which is, as I already mentioned, you need to be very, very careful. You need to use proper appropriate solar filters if you are going to capture the sun, and you need to use appropriate solar goggles if you want to observe the sun. So these are taken during the solar eclipse, and then these photos are put together in a collage. So for mobile astrophotography or mobile photography, you can use these softwares. So they can be used to process images, and a lot of camera softwares are nowadays available to acquire beautiful cell phone images. Many modern mobile phone cameras come with astrophotography mode or pro mode, which allow you to capture large exposure photographs. So these are 32-second exposures, and multiple exposures have been put together to get these star trails using phone. And this is a one single large exposure using a phone. So these are some deep sky photographs that I have captured using a DSLR camera, which is attached to a telescope. So it is very, very easy to capture photographs like this. And with the right kind of practice and the right kind of technique, you can process these images and you can produce some beautiful results. So these are some more examples of astrophotos taken using a DSLR camera and a telescope. The aperture of the telescope used is 8-inch, so it does not require a very, very large telescope also. But yes, traveling to a darker location away from the city definitely helps. Some more images. This is the Andromeda Galaxy. This is the Orion Nebula taken with a wide field. This is the M45 or the Pleiades cluster. On the left hand side, there is Andromeda again. So these are some photos taken with a cell phone. So different processing techniques can be used, different image acquisition techniques can be used, and you can produce different results. So this is pretty much the end slide. So to summarize how to do astrophotography, the most important thing is to basically start. So many times you often get discouraged by feeling that you have inadequate gear. Maybe you are not very skilled, or maybe the weather conditions are too bad. So you can find as many reasons as you can, but the best way to start is really start. And the fastest way to learn is through trial and error, is what I believe. Because many times when you wait and learn through the tutorial videos, it does take a lot of your time. So the best way to start is actually start capturing photos. Maybe some of your photos will be wasted, some of your efforts will be wasted, but it will help you see the results firsthand by trying out different camera settings, lens settings, and then you can also give a good amount of practice over post processing, by which you will be able to acquire some excellent results. So that's all about the astrophotography as well as the demonstrations that we wanted to show today. We really wanted to show you a demonstration of photometer, as well as we wanted to show you sunspots and craters. But the weather conditions are really poor today. So we were able to show you some of the earlier photographs we had captured instead. In the last session, we have already demonstrated how to attach camera or mobile phones to your telescopes. And if you do not have a telescope, how can you do astrophotography without the use of telescope, but the simple lens and basic accessories that you get along with anyway? So if you want to ask us any questions, you can write to us at psychop@gmail.com. These are our social media handles. We also have an Instagram page now called IUCAA. And you can always write to us or ask questions on the Slack channel as well. We will also be able to answer the questions over there. But if you don't have any questions right away, you can write back to us on cypop@gmail.com. If you quickly want to unmute yourselves and ask questions, please feel free to do that. You can raise your hand, you can unmute yourself and ask questions. So please go ahead. It seems that no hands have been raised, so I take it that there are no questions right away. So thank you all for listening. I'm sorry for extending the talk a little bit because the demo often takes a little bit longer, and there are too many astrophotographs and too much information was given in a very small amount of time. I'm going to share this presentation with you, but probably Debarati will share it on the Slack channel. So if you don't have any questions, I think we can conclude this meeting. So if you have any questions, you can either quickly post it on the into the chat box or just simply unmute yourselves and ask the questions right away. So it seems there are no questions. So thank you all again. I'm going to stop the recording and end the meeting now.